Hello everyone, welcome to machine learning. This is my first experience using a tablet. So let us see how it goes. COL774 machine learning, March 20. Well, we will do it by the date that maybe you should watch it. So let me call it March 31st. March 30. Oh, I'm sorry. That March 31st would be Tuesday, 2020. Uh, Before we start, I hope all of you are doing well at home uh, and safe with families as instructed by the director. So we'll try to do video lectures mm, uh, for our class. I guess some IITs have simply declared this as a summer vacation and then they'll start later. But in any case, for us, the instruction has been to do this in the form of video lectures. So let us see how it goes. As I said, this is my first sort of experience with video lecture using tablet PC. So we're with any possible hiccups. But I'll try to do it as smooth as we've done in the class. Let us see how it goes. Okay. So we'll start a new topic today, which is neural networks. Some issue here, neural networks, right? And what is the idea, right? So the idea in neural networks goes long back to the history of artificial intelligence, right? Right, and these are the times when even I would say, machine learning took the modern day form, and people were really grappling with the idea that how could you construct artificially intelligent beings, right? And one way to really understand that was to think about human brain and try to simulate the behavior in the brain, right? And as many of us know, and as the modern sort of science of brain tells us, that the most simplest model of the brain, right, this is my simple picture of a brain, right, is that of a neuron, right, which is the basic unit of computation, which takes bunch of inputs. Let's call it x0 to x1, and then this neuron fires, x0, x0, x1 up to xn, and this neuron fires or not fires, right? So if it's some of its inputs is more than a threshold, then it fires and outputs 1, otherwise 0. And this is the thresholding function, which takes a linear combination of its inputs. Let me call it theta transpose x, uh, where g is simply the indicator function of theta transpose x being greater than equal to c. Right. So this is the basic idea of neuron, and these neurons are are supposed to be constructing the the basic unit of computation in the brain, and there could be maybe millions of neurons in the brain, in human brain. And what is impressive is really the amount of parallel computation that they can achieve with billions of interconnections, right? So each neuron, as we'll see, does a very simple computation, which is simply this sort of linear operator that I've not defined. This typically this will be, well, I've defined it here, theta transpose x, which is nothing but theta j x j, j equal to 0 to n, right? And as before, x0 is 1, which is sort of the intercept term, right? And theta 0 is the coefficient of that intercept term, right? And if you were to write it, you could also write it as theta j x j summation over j equal to 1 to n is greater than equal to minus theta 0, right? So this can be thought of as the threshold that you really worry about, because x0 is 1, right? X0 is equal to 1, right? So this is another interpretation that the sum of all the inputs, right, other than the intercept, should be greater than equal to this threshold minus theta 0, right? So these two are one and the same thing, right? So if this holds, then the neuron fires, right? So this is the basic um, sort of computation in the brain, um, right? And I guess I've already described why this is really relevant for the history of AI, because people thought that if we could really simulate the behavior in the brain, then we would be done, or at least we would make a significant step towards constituting or constructing artificially intelligent beings, right? But which was not really the case, as we'll see, right? But nevertheless, this zeal, or this whole effort to replicate or simulate the behavior in the competition, has gone a long way in terms of building very powerful machine learning systems. In fact, these neural networks also form the basis of modern day architectures or modern day machine learning algorithms, which have become fairly popular, or almost de facto standard, is the deep learning models, right? And right after the lectures on on neural networks, we will learn deep learning models, right? That is to become, that will be coming in let's about a week or so. O- okay, so let's move forward. Let me see how I can save this slide. I think this should be auto saved, so let me just move forward. This is slide number 1 maybe. And just to move a little bit fast forward, and these basic perceptrons, these units are composed in a neural network in a layered by layer fashion. So this is, let's say, layer 1, which gets all your inputs. Each of these perceptrons in layer 1 will get all your inputs from x0 to xn repeated, right? And then layer 2, which will, whose inputs will be outputs of layer 1, right? And then up to, say, let's say, layer n minus 1, which is, the penultimate layer. And finally, these might go into the final layer, which is your output layer, which we can refer to as layer n, right? And this is, your final function, um, which is essentially composition of all these perceptrons working, one after another, these layers working one after another. And this could be as complex as, this neuron could essentially, in your brain, could be a neuron which, let's say, recognizes, your grandmother, right? So this fires, or this is one, if this sort of composition of over all these inputs essentially makes this neuron fire, then right, you say that the image was essentially of your grandmother, otherwise you say no, right? And this compositionality is really the key to this compositionality is really the key to the power of neural networks, and also the modern day deep learning systems, right? And as we looked at on the previous slide, each perceptron is a very simple sort of unit, which implements a linear classifier, which is theta j xj summation j equal to 0 to n, right? And there is this thresholding function, right, which can be thought of as g of z, which is, g of theta transpose x, which is nothing but indicator over theta transpose x greater than equal to 0, right? In this form, h theta x can be thought of as this g of theta transpose x, and this is called the activation function, right? I think I might have mentioned this in the previous slide also, right? So in this regard, if you think about it, this is similar to what we have studied earlier. Other, you think about comparing this with things like logistic regression, right, or SVMs, in the most basic form, which were also linear classifiers. The h theta x, for example, for logistic, would have taken a slightly different form, where we are dealing with probabilities, but in order to do the final classification, this is still an indicator over theta transpose x being greater than or equal to 0 not, right? So in that sense, it is a linear classifier, and as I explained on the previous slide, you can also think of this function implementing this sort of thresholding over minus theta 0, right? But okay, so to understand the perceptron better, we will first look at uh, the problem of representing very simple Boolean functions, right? And this might seem almost like a I wouldn't say trivial, but very simple exercise. But this will give us a fair amount of idea as to that very simple functions such as XOR are also not representable by a perceptron, and that will also motivate very well why do we really need to go to multi-layered neural nets, right? So let us consider a very simple function, which is the AND function, which is given by this fx is x1 and x2, which is sort of the standard Boolean operator, where x1 and x2 belong to the standard Boolean domain 0, 1. And in particular, we are looking for h theta x, which is the indicator of theta 2 x2 plus theta 1 x1 plus theta 0 ln equal to 0, uh, and which is equal to 1 if and only if x2 is equal to 1 and x1 is also equal to 1, right? So this is our end function, and to show this pictorially, let us look at this diagram where this is x1, this is x2, and this is 1, this is 1, and this is the only positive point, which is 1 comma 1. This is a negative point, this is a negative point, this is a negative point, and we are looking for linear separator, right, for these points. And as you would agree that there are infinite many such separators which separate positive from negative, and one such separator is probably this line that I'm drawing here, which goes through points 1.5 and on the x2 axis, and also the point 1.5 on the x1 axis, right? I guess it's not really drawn to the scale very well, um, but that's okay, right? And what are the coefficients, right? The slope of this line is -1 and the intercept is 1.5, and you could essentially write this line by noting that theta 2 is 1, theta 1 is 1, and theta 0 is -1.5, right? So if you write this line in the form of y equal to mx plus c, you will get the slope -1 and intercept as 1, right? Another way to look at this is these coefficients are such that only when both x2 and x1 are 1, this linear composition is more than 0, otherwise it is less than 0, and which is basically what we require from the AND function, right? Similarly, think about what might be sort of these parameters when representing, this is our AND function. Think about what might these parameters be when representing the OR function, right? So in this case, right, maybe I'll not draw this line explicitly, but uh, or let me just draw it, right? So let me just draw it here. This is x1, this is x2, and this is 1, this is 1. And in this case, this line should be passing uh, through these point 5 intercepts, and anything above this line is now positive, and anything below this line is negative, which is essentially 0 point, right? And in terms of the thetas, right, h theta x is again theta transpose x, right? H theta x is indicator of theta transpose x greater than equal to 0, and one possible way of writing theta 2, theta 1 and theta 0 is theta 2 is 1, theta 1 is 1, but theta 0 is now minus 0.5, right? And you will see this satisfies the OR function, right? Right, as you can see, there are infinite many such lines which which can realize these separators, but this is one such separator that okay. Let's move forward. Uh, Let me see. This is fine. For fun, for fun, let us do one more. Suppose we want to do NAND, right? Which is not of and right. This representation would be this point 0 0 is the only positive point now, and 1 0 1 1 and 0 1 are all negative points. And the separator again will be right, one of the separators is this, but in this case this side is positive and the other side is negative, right? And as you can see in this case, if h theta x is theta transpose x is greater than equal to 0 indicator of this, then you can choose theta 2, or I guess if it is corresponding to this figure on the left, then theta 2 is minus 1, theta 1 is minus 1, and theta 0 is zero point 0.5, right? Which is saying that only if both theta 2, x2 and x1 are 0, then this function this function is this theta transpose x is greater than 0, otherwise it is less than 0, right? So this is the line function. And homework for you, which is not very difficult, is I would ask you to implement a perceptron which implements simply this not function, not of x1, right, where you will have only two parameters, theta 1 x1 plus theta 0 greater than equal to 0. Indicator of this will be your hypothesis function, and you want this to represent your not function, right? So please this. Okay. So moving forward, right, this is fine, but moving forward, let us think about an interesting function which cannot be represented by perceptron, which is the XOR function, right? And what is the XOR? Remember, this XOR function is one if and only if uh, exactly one of x1 and x2 is is 1, right? So this XOR is parity function, which is saying that either you should be in the state 1 0 or 0 1. Only then, in fact, this function is true. Otherwise, it is false, right? And let us look at it diagrammatically on the next slide. Okay, so XOR function is interesting because this is a function which is not linearly separable, and let's see why. So this is x1, this is 1, and this is x2, this is 1, and this is positive, but this is negative, and this 1 point is also negative. And as you can see, there is sort of no linear separator which separates positives and negatives, right? Right, because you could think of a line going through 1001, but the problem is, right, what do you do the points on the line, right? If you tell them to be positive, then 1 1 would also be positive, and if you tell them to be negative, then anyway that doesn't work, right? So you can verify that there is no linear separator which can actually realize this XOR function, right? This is the XOR function, and that's a problem, right? So this cannot be represented by a single perceptron. Right. So this leads us to further analysis, or further going deeper into the theory of neural networks. Then the question might arise, okay, you cannot represent this using a single perceptron, but you can you compose multiple such perceptrons to get or to realize this XOR function? And the answer is yes. And the way you would do this is realizing that XOR can be written in multiple such forms. So one possible form would be not of x1 and x2, or not of x2, or let me write it slightly differently, x1 and not of x2, right? And this is essentially and over not of x1 and x2, which can be represented using a perceptron. In fact, that probably will be homework for you. This is also and over x1 and not x2, which can be represented, and then we are composing this using an OR function, right? So how will this architecture look like, right? So we'll have three perceptron units, right? And there are two layers essentially, right? So this gets x0, x1, x2, and this gets also get x0, x1, and x2. This implements the function, right? And this implements the function not of x1 and x2. This implement the function x1 and not of x2, and these two feed into this OR unit, which is essentially, if I call this as y1 and I call this as y1, y2, then this simply is doing y1 or y2, right? And this is my output. And while showing this, note that I have sort of hidden the thresholding unit inside these boxes, right? And I'll just give you one of these um, functions. I guess I moved on to the next slide, but that's okay. I'll give you just one of these functions, which is, let's say, not of x1 and x2, right? If you were to represent this, using h theta x is indicator of theta transpose x is greater than equal to 0, then one possible value of theta 1, theta 2, and theta 0 would be anyone. So theta 2 is 1, and theta 1 uh, is, just give me a minute. So theta 2 is 1, theta 1 is -1, and theta 0, what do you think? Right, so we want this to be uh, 1 if x1 is 0 and x2 is 1, right? So you can verify that theta 0 is 0.5, right? And this is because the Boolean domain is 0 and 1, right? So you can verify that this actually implement this not x1 and x2 function. So similarly, you figure out how to implement x1 and not x2 function, and then finally you can implement XOR as y1 or y2, where y1 is not x1 and x2, and y2 is x1 and not. Okay, very good. Right, and okay, so we will proceed forward. Right, so this is really the key to compositionality, that although one perceptron cannot learn it, but with a combination of three perceptrons, we are able to learn XOR function. And think about the minimum number of perceptrons required to learn this XOR function is actually 3. Right, and think about why we can't do in number of perceptrons which is less than 3. Okay, so this is fine. Right now, before we go to compositionality, this was just to understand the power of representational power of the composition. Now let us try to understand how do we learning the parameters, how do we learn the parameters of a perceptron, right, in the next slide. Okay, so this is our next slide. Let me Right. So we'll present, right. This is for historicity and also to understand and motivate the further learning problem. We'll implement, or we will show what is referred to as the delta rule. And remember, what are we trying to learn? We are trying to learn, these are our inputs, and there is a linear combination of these inputs which happens, which is theta j x j is equal to 0 to n. And there is this thresholding unit, which is the activation function, which is g of z, which for now uh, is 1 if and only if theta transpose x is greater than equal to 0, right? And z is nothing but theta transpose x. Later on, will use different activation units, which are sort of differentiable. So one issue, as I already pointed out, with this particular activation unit, is that it is not differentiable. That is one. And also, not only that, there is a problem because if we try to to pass the gradient through this, then the gradient is zero at every point, other than at z equal to 0, uh, where it is not defined, right? So this particular activation unit cannot uh, pass gradients, right? Why? Because if you see that this is really flat when theta transpose x is less than 0, and also flat when theta transpose x is greater than 0. So at any of those points, right, for there is no way for the learner to really know that which direction to move in, and that is a problem with this particular kind of activation unit, and we'll make it smoother later. But let us now look at a very simple, more like a heuristic learning approach, which is called the delta rule, and it makes certain assumptions for it to really work. One is that linearly separable data, right? So the data should be linearly separable, and other is more sort of algorithmic. Eta is the learning rate, if you will, uh, is sufficiently small, right? I'll describe what the learning this learning rate is, and this is the case. Then we can actually describe this delta learning algorithm, which is on the right hand side, which is theta 0. You init the parameters somewhere, okay? Then t is equal to 0. This is fine. Then until all the points are correctly classified, which is there exists an I such that yi is not equal to h theta uh, t current parameters xi, right? So as long as there is a point for which h theta using the current set of parameters is not equal to yi, you do the following. You move a little bit in the direction of uh, that point. And what does that mean? That means that theta j t plus 1 uh, takes the value of theta j t, which is the old value, minus or plus eta into yi minus h theta xi, uh, using current set of parameters as theta t xi into xi, and that's essentially it. Well, t goes to t plus 1, and that's it, right? So this is your delta rule. What is it saying? It is saying that, if assume for now that that uh, let me see, this should be xij, sorry. Yeah. So assume for now that xij is positive. So what is it saying? That if your yi is more than h theta xi, then you have to bump up theta j parameter. And this is for all j, right? So you would do this for all j, and then essentially, right, those will be your new set of parameters, right? So note that you compute this theta j at t plus 1 for all parameters, using the last set of parameters theta t, right? This is similar to what we do in gradient descent. Right? In fact, if you look at it, if you look at the right hand side, right algorithm, which is essentially the delta sort of rule, it's very similar to the update for gradient descent for logistic regression, um, or even linear regression. In fact, the probably the whole class of GLMs, the only difference is h theta xi is a linear combination followed by this the step function, right, which is a sort of non-differentiable. Nevertheless, you can show that this delta rule converges uh, for linearly separable data and when eta is sufficiently. Okay, but this is a problem because you know there's two problems. One is not very principled, right? I mean, this sounds like more like a heuristic. We would really have something which is more mathematically grounded. Ideally, would like to have gradient descent. I mean, this seems similar, but this is still not really gradient descent because there is no gradient as such, right? Because of the step function being used as an activation function. And this, the other problem with this is that this does not work when data is not linearly separable, right? And that's a problem because we would still like to learn a reasonable function, right? Even if right, there is some noise in the data, right? And right. And we know that there is a linear separator which actually works well for the data. Okay, so given this, right, let's move forward. Okay, so let's move forward. Right, so what is the solution, right, to this problem of not being able to use essentially delta rule, right, because of the problems, right, challenges that I just cited. And if you think about it, the actual problem with our learner is this activation unit, right? This g of z, which is this indicator of theta transpose x greater than equal to 0, right? And which is a step function, right? And that's a problem because the gradient doesn't flow through this, right? This is going from x to xn. This is implement, right? And z is equal to theta transpose x here. Okay. Um, so as you will see, what comes to our rescue is again this function that we have seen earlier, which is essentially the sigmoid function, which is we'll replace the step function by this sigmoid function instead, which is of this s-shaped function, and we had used this earlier for the case of logistic regression also. This is g of Z and Z. There it was used for a different purpose because we wanted to squish everything between 0 and 1. Um, and here also you will see that this squishes everything between 0 and 1. But here the interesting thing is, as we can look at the shape of this function for very large values or in fact for the large values of theta transpose x, it quickly goes to 1. And right, as z goes to for z greater than 0, theta transpose x or g of z quickly goes to 1, and for g less than 0, right, z of z quickly goes to 0. um, right, and this is nice because we still get sort of this step behavior. I mean, not exactly around x equal to 0 or theta transpose x equal to 0, that equal to 0 is it sort of behaves linearly, but as soon right, the moment we move away from z equal to 0, this function on the right side it goes to 1, and on the left side it goes to minus, it goes to 0, right? And which is a nice property that can be utilized. So for right, to approximate the step function by this sigmoid function, and what we get in return is that now our entire objective will be differentiable, and we can actually use gradient descent, right? So given this, right, what will be our h theta x? Let me write here. H theta x will now be g of theta transpose xi, right? We don't have to use the indicator function. Now, right, this h theta x is between 0 and 1, and if it is more than 0.5, we'll say uh, the label is positive, and if it is less than 0.5, we'll say label is negative. And g now being sigmoid function, this can be written as 1 over, uh, there is no xi here, this is simply g of theta transpose x, and this is 1 over 1 plus e to the minus theta transpose x, right? And if you remember, if you recall, this is very similar or identical to logistic uh, regression. There also we use h theta x to be of this form, but here there is no probabilistic interpretation, right? There is no probabilistic interpretation in case of neural networks, right? Or at least as of now, right? There is no probabilistic interpretation. Maybe later on we'll come to that. Okay. So how do we really learn this, right? Given that this is our h theta x, how do we learn this, right? So learning now can proceed with gradient descent, um, right? So learn using gradient descent, uh, but for that we have to define, an error function. Remember, for logistic, it was negative of the log likelihood, which was the error function, right, where we interpreted this h theta x as the probability of being 1, and we defined the log likelihood, and we optimized with respect to theta, and we said, we want to r min theta of ll theta, right? Uh, but for the case of neural networks, we because there is no probabilistic interpretation, we will instead define our error function. And error function will be simply a squared error, which will be yi minus h theta of xi whole square, I equal to 1 to m, right? And then we can sort of do the average squared error, multiplying by 2m, right? And I will encourage you to contrast this the with the objective function for logistic regression, right? Which very different form, because it was a log likelihood objective and not based on the squared error objective, right? In fact, we use the squared error objective for linear regression, um, and we are using the same here, but the form of h theta x here is different because it is essentially the sigmoid function. Okay, so now let us try to quickly understand the form of the gradient descent. So for that, we have to compute the gradient delta theta of the theta. What is it? So this will be half I equal to 1 to m of 2yi minus h theta xi into delta theta of h theta xi into minus 1. Okay, now h theta xi is g of theta transpose xi, and we also know, as an aside, delta z of gz, right? I will not derive it again, is simply g of z into 1 minus g of z, right? This is derivative of a sigmoid function, right? And we will use this property to find the gradient of g of theta transpose xi. will be We'll differentiate this first with respect to theta transpose xi, which will give us g of theta transpose xi into 1 minus g of theta transpose xi into delta theta of theta transpose xi, and this quantity here is nothing but anyone, this would be simply xi, right? A derivative of A transpose B with respect to A, gradient of A transpose B with respect to A is B, right? So this is simply xi, right? And if this is the form, then we can write the, so let us write the complete gradient of j theta, which is yi minus h theta xi whole square I, let me erase that, I equal to 1 to m 1 by 2 m, where h theta xi is g of theta transpose xi, which is the sigmoid function, uh, which is 1 over 1 plus e to the minus theta transpose xi. Okay, therefore the gradient of j theta can be written as 1 by 2 m I equal to 1 to m of yi minus h theta xi into minus 1 into h theta of xi into 1 minus h theta of xi, and this is coming from the derivative of the sigmoid, these two terms, into xi, right? And note that this term is an extra term, right, if you will, compared to logistic regression, and this comes out to be there because of the different form of the uh, the objective function. And also note that in this case this is highly non-convex, right, because of the form of the h theta function, right? But nevertheless, this is our gradient, and given this we can use standard gradient descent update rule to learn this, to learn the parameters of a, let me see if my marker is having some, to learn the parameters of a perceptron. I think my marker is having some issue. Let me move on to the next slide. Let me write this on this slide. Given the gradient that we obtained on the previous slide, um, then the gradient descent algorithm uses the following update. It is a standard gradient descent update, which is theta t plus 1 is theta t minus eta, which is the learning rate, times the gradient of the objective function evaluated at the current setup, right? And this is sort of your update, and then you repeat this while not converged, right? And of course there is an initialization that also happens, which I have not written here, right? And this is sort of the entire update equation, and the convergence is similar to what we have discussed earlier in the context of logistic regression and other algorithms, right? So this completes the learning for a perceptron, right? Now the next question is, how do we really extend this to more interesting case of a multi-layered neural network, you know, where all these perceptrons are arranged in a layer by layer fashion in the manner that we had seen earlier in one of the slides. these are the inputs, and these are different layers of units, finally leading to an output layer. This is O1 to OR, right? So we will uh, divide this problem, uh, right? So this is our structure of the neural network, where we have this x0 to xn feeding into all the inputs, all the perceptrons in the first hidden layer, and going all the way to the output layer, right? And everything here which is sort of hidden from the output is called the set of hidden layers, right? Because they are hidden from the set of the final layer, which is the output layer, and there could be any number of such hidden layers, and the final layer is the output layer. So we will do learning in this context of the parameters. Before we break for the next class, let me describe one more thing, which is our error will be in terms of the entire set of parameters in the multi-layered network, right? And how will it be defined? It will be defined as yi minus uh, o, right? Note that now there are multiple outputs, so there will be, let's say, r such outputs. So we'll index. Let us index them by L. So therefore yi L minus O L square summation over L equal to 1 to R, and summation over I equal to 1 to M, right? This will be our objective function for multi-layered neural network, where there are R output units, right? So this is simply the squared error over the sum of squared error over all such R such output units. And in the next class we will see that we will do it for the simple case of m equal to 1, right? Only to simplify the notation. This is only to simplify the notation, right? And whatever we derive can is easily or directly extensible to the case of multiple examples, because we can just take a sum outside, right? And our goal will be to compute delta theta j theta for two sets of parameters. One will be parameters in the output layer, and this will be parameters, the second set of parameters, which are parameters in the hidden layers. And why do we really separate them out? Because as you can see, the YILs, the outputs that we or rather OLs, are the output that we produce, are essentially directly dependent on the parameters in the output layer, but they are indirectly dependent on the parameters in the hidden layer. So we'll separate this out in while computing the gradient. And before we break, finally, the j theta that we are talking here will be a simple form where L equal to 1 to R of y L minus O L whole square, right? And because we are assuming m equal to 1, right? Okay, I think I should stop here, and we will continue in the next set of presentation.